We're going to start now with section 11.3 on page 544 about a hypothesis test for the difference between two means when we have the case of pair samples. So remember the pair samples case is when you have a sample where the individuals might be just the result of before and after treatments. So in some sense the first sample and the second sample are related. So let's say you have a population and we are extracting a sample. This is my sample 1, and this is for example a group of individuals that are just part of that population. Then I'm going to use that group of individuals to apply a treatment. So, and I'm going to measure something after the treatment. So I'm going to get a sample 2, which is with same individuals as sample 1, but with the difference that this is the after treatment measurements, and this is the before treatment measurements. So we're going to try to know now whether this sample still belongs to this population or maybe now belongs to a different population. So that's the purpose of this test, to see whether we get some effects for doing some experiment or treatment. So the process is that now we're going to have our sample 1, the measurements, then we have measurements from sample 2, different kind of values here. So the way that we're going to deal with this problem is that we're going to compute the differences between the measurements. So we're going to create a new sample with the difference. So this two sample table is going to become just one table with the difference for all those different individuals. And then we're going to work only with the difference as a single sample. So the steps are going to be the same as before. We can check also our book. So we can see on page 544 the assumptions to conduct this kind of testing. So we need to have a simple random sample of match pairs, and either the sample size is larger than 30, or the difference between the items in the match pair shows no evidence of strong skewness and no outliers. So in other words, that the differences follow a normally distributed distribution. So those are the assumptions that we need to satisfy in order for us to use the method that is going to be now described. So the method is described on page 545. So again, we start with setting up the hypothesis, the null and the alternative. Then we need to get the information about the significance level that we're going to use to make the decision. Then we're going to compute our test statistic. Our test statistic T, in this case, because we are comparing means, is going to be based on the differences. So we're going to get the mean of the differences, and we're going to get also the standard deviation of the differences, and the rest is the same as we were before. So let's try to answer a problem. So we have here a summary also in the same way that we have been performing our test. So we're going to write the claim, the null, the alternative, then we're going to get the alpha level. Remember, if you don't have the alpha level given, then you need to set that value equal to, that alpha equal to 0.05. Then we compute the test statistic. This is the formula again, based on differences, the mean and the standard deviation of those differences. Then we're going to compute our p-value. Remember, we have two ways to make the decision. Either you compute a p-value or you compute critical values, and then you see whether this value that you're going to obtain here is within the interval between the minimum and the maximum critical values, or outside. If this statistic is inside of the interval of the minimum maximum critical values, then you are in favor of the null. Otherwise, you need to reject the null. On the case that you are computing the p-value, then computing the p-value is just computing this area here under our curve, and we're going to have two possible scenarios: either t or t statistic is positive or negative. If the statistic is positive, then you're going to use 1 minus pt, and the input values are going to be your t and the degrees of freedom. And if the test statistic t is negative, then you're going to use just pt of t and degrees of freedom. So this is very similar to the hypothesis test of a mean. Remember, we covered that in the previous chapter, and we use also the student t distribution. Then you make a decision. If you're using the p-values, then you just check or compare your p-value to alpha, and if the p-value is less than alpha, you're gonna reject the null. So we're gonna solve example 11.5 on page 545. So let's see. We're gonna solve a problem here. So let's read the problem. The problem is that we're gonna test the null where the mean of the differences is gonna be 0 versus the alternative hypothesis where the mean of the differences is greater than 0. To do that, we're going to use the data in table 11.1, and we're going to use a significant level of 0.01. So we need to check then the table 11.1. So let's see. We have 11.1. The table is over here. So you can see here. So you're measuring gas mileage before and after tuning up automobiles. So first we have before the tune-up, you have this measurement, that's the second row. After the tune-up, you have the measurements on the first row. So the first step is that we're going to compute the differences. Since they are indicating us to use table 11.1, they already computed the difference. But in the exam or in the quizzes that you're going to solve later, you're going to have only usually the first two rows. You can write this in this horizontal format, or you can write this in a vertical format. So the first column might be just before tune-up, the second column might be after tune-up, and the third column might be the difference. So the important thing is that you need to compute the differences to be able to conduct the test. So the way that we're gonna do it, if you are using R, then you need to enter your data sets. This is, for example, let's say that you don't have the differences yet, so then you're gonna create a first variable. You can write that before, and then you're gonna enter all the corresponding values for the first case when you have your car before the tune-up. So you're gonna have 33.76, 34.30, and the last value is gonna be 31.25. Then you're gonna get another variable, is gonna be after the variable after. You're gonna enter 35.44, comma 35.17, and so on until you get the last value, which is 32.39. Then you're gonna compute the differences. You're gonna say the difference is gonna be just after minus before, and this is gonna be your differences. Then you just compute the mean and the standard deviation. So the mean is just the mean of the differences. The standard deviation is just SD of the difference. So this is the information that you need to process for you to get the information that you're gonna need to to solve the problem. Okay, so but let's start from the very beginning. So you need to set up your hypothesis. So they are giving us the hypothesis. The null is just the mean of the differences is going to be equal to 0. So that means that there are no effects from tuning up the car. So the treatment in this case is just the tune up. So, and then the alternative is that you're expecting the difference to be greater than 0. So this is like saying that the mileage is gonna improve. So in this case, you're gonna get greater mileage after tune-up. The mileage is gonna be greater. You're gonna get more miles per gallon of gasoline. So that is gonna be, this is after the tune-up. This is before the tune-up. So you expect to get more yield from your gas. So from the alternative, you're gonna see that this is a right tail test. So that means that you're gonna have something like this. So let's compute then the differences and also the mean and the standard deviation to be able to conduct our test. Alpha in this case is given and is 0.01. So that's the significant level that is provided. Okay, so let's do this computation. So let's use our console to start our computations. So let's see, we're gonna start with computing everything from scratch in the same way that you will do it if you are given just two data sets. So before we have 33.76, 34.30, then 29.55, 30.90, then 24.92, then 21.78, 24.30, and finally 31.25. So that's my first data set. Then the next data set is measurements on the same individual. So that's the reason this is a paired sample, because there is a relationship. So I have 35.44, then 35.17, and 31.7, 31.57, 26.48, 23.11, 25.18, and finally 32.39. So I have two data sets, so I'm going to compute the difference now. The difference, I'm going to write this as the difference. It's going to be equal to, we say that we're going to have after minus before. So, and I can call back the differences. So I got 1.68, 0.87, 152, 0.67, 156, 133, 0.88, and 1.14. So that's the new sample, essentially. So now I'm going to compute the mean of this sample, which is just mean of the differences, and I'm going to compute the standard deviation of this new sample. So I'm going to take note of those values. So I am getting the mean of the differences is just 1.2625. The standard deviation of those differences is 0.3731,693. So let me go back to the notes for you to see the next computations. So I have here the mean of the differences, the standard deviation of those differences. So the next step is just computing the test statistics. So we're going to compute t. So we're going to compute the test statistic. So by using the information from the sample. So now it's just this is just one new sample. So t is going to be just the mean of the differences minus the mean of the population of differences over standard deviation and the square root of the size of the sample. So from here you know that the mean is just 1.2625 minus and the mean of the population of difference is going to be 0 because we expect no changes, no effects from the tune-up, and then the standard deviation is 0.3731693 over the square root of 8. So I'm going to compute now this information. So it's good if you use parentheses to enclose your numerator and denominator to prevent mistakes. So let's do that now. So I open my first parenthesis and I write 1.2625 minus 0, close the parenthesis, open a second parenthesis. I'm going to divide 0.3731693 over the square root of 8. So this is going to be equal to 9.142741. So that's my test statistic. Now the next step is just we're going to compute our p-value. We can compute critical values if we were trying to solve this problem by using critical values. So if you are using critical values, you know that you're going to use alpha to find, in this case, the alpha. So essentially you are saying that you know that this is alpha equals 0.01 and you want to know this boundary between the region that favors the null and region that rejects the null, which is this region. So and your t alpha, remember you're going to use a qt function where you're going to write here 1 minus alpha and degrees of freedom, which is n minus 1. So if you want to know this critical value, you use enter qt of 1 minus 0.01, comma 8 minus 1. And then you're going to get your t alpha to make the decision based on critical values. If you want to use a p-value method, then what we're going to do is that we're going to use our t that we just found from this step. So this is the t that we're going to use, and we're going to find this area. This area is going to be a probability value. Since t is greater than 0, since t is a positive value, then this is going to be just 1 minus pt, or test statistic, degrees of freedom. So it's going to be 1 minus pt, and t was obtained before 9.14, 2741 degrees of freedom, a minus 1, similar in the previous step. So from here we're gonna get a p-value. Then we're gonna make a decision, and the decision is gonna be the same, either using critical values or using a p-value. So let's compute these values to be able to finish our problem. So let's go back and work on our R console. So if you are trying to look the critical value, so you're gonna write qt of 1 minus alpha, which is 0.01 comma degrees of freedom a minus 1. So that's your critical value that you're gonna use to decide whether you get a value that's in favor of the null or against, or to reject the null. So the critical value is 2.997952. Now the p-value, let's say that you are using the other method, so you need to compute 1 minus pt, because this is a right tail test. So you're gonna have the p-value that you found before, 9.1427 41 comma degrees of freedom a minus 1 again. So now we get a very small value, 1.925141 times 10 to the negative 5. So those are the values that we obtain, and we're going to use those to make a decision. Remember, the decision is going to be the same. So if you are using the critical value method, then you just plot your test statistics. So you find first the critical value is here, is 2.99. That's the critical value. So this region is in favor of the null. This region is to reject the null. So then you use your t, the one that you found, 9.14. So what is 9.14? 9.14 is going to be somewhere over here. So let's say it's over here. So your t equals 9.14 is very, very, very far from the region that favors the null. So you're going to need to reject the null. So that's the conclusion, the decision that you're going to make using the critical value method. Using the p-value method is going to be the same thing. You need to compare your p-value with alpha. So alpha is 0.01. So using this information and this information, you can see that your p-value is very, very, very small compared to alpha. So the conclusion is, when p-value is less than alpha, you reject the null. See, in both methods, you're going to get always the same conclusion. If you are not sure of your work, then work on both methods in the exam, and you should get the same answer. If you get a different answer, maybe you did something wrong in one of those two methods to make your decision. So the last step is just we're gonna make our decision. We're gonna write our conclusion. Actually, the decision is reject the null. So you're gonna write something like, there is enough evidence to reject the null. So there is enough evidence. Now you know that the null and the claim are different. So the claim is that you got more mileage from tuning up your car. So and in this case, you just need to rewrite your conclusion as, there is enough evidence to, and since these are different, you're gonna switch the verb to support the claim that, and then the claim is there, just that mu d is greater than 0. So tuning up the cars increases the mileage your mileage, your gas mileage. So that's the final conclusion. So now you're going to work a problem. Problem is from section 11.3, exercise set on page 551. You're going to solve problem 10. You're going to send me your answers. You're going to upload your screenshots from your work on through Canvas on the corresponding class Word section by clicking on the submit button. So let me just show you the problem, and then we're going to start later the last section that we're going to cover from chapter 11. So here, problem 10 is over here. So you are given two data sets. So you're going to need to compute your differences, and then also the statistics, the mean and the standard deviation. So you are comparing scales. So it's an experiment to determine whether there is a systematic difference between the weights obtained with two different scales. So 10 rocks were weighted. So you are using the same individuals. You use a rock in one scale, then you weigh the rock in the other scale. So you essentially have the same individual before and after switching scales. So you have here the data that they collected, and then you just need to state the null and the alternative hypothesis. You're going to compute your test statistic. So, but before that, remember, you need to compute the differences. And then using an alpha level equals 0.01, you're going to make a decision. So that's the problem. Just work on that and send me your answers. We're going to continue now with section 11.4 on page 553 about hypothesis tests for two population standard deviations. So this time we have a population 1. We're going to extract a sample. That's going to be my first sample. Then I'm going to collect another sample. And now I want to know whether this sample, in terms of standard deviation, belongs to the first population or maybe belongs to a different population. So to do that, we're going to use a new hypothesis test. But first, to be able to use the methodology, we need to comply. We need the problem to satisfy two assumptions in this case. The first one is that we have independent random samples from two populations, and the second one that both populations are normal. These assumptions are on page 553 in your book, and then on the next page, actually on page 555, we have the corresponding blue box with the steps that we follow to solve these problems. So the first step is again the same thing. We set the null hypothesis, we set the alternative hypothesis, then we find or set the level of significance alpha. Then in the next step we're going to compute the test statistic, and this time we're going to use a new one. We're going to use statistic F. F is going to be defined in terms of variances. Then the final step is just computing either critical values or p-values to make a decision, and then at the end we just write down a conclusion. So in terms of the methodology that we have followed so far, what I have here is kind of summary of the same kind of things that we have been doing so far. So our first step is usually setting up the claim, the null, the alternative, finding alpha or setting up alpha, then computing the test statistic that we're going to use. This time F is going to be computed by dividing the variance, the larger the largest variance of the two samples over the smallest variance of the two samples. So we're going to need to compute the variances if we have data sets, or if they are given, just compare those variances. The largest one goes into the numerator, the smallest one goes into the denominator. So because of this condition of always writing the largest on the top, we're going to have always a kind of right tail test in terms of the computations for p-values or critical values. But again, depending on the alternative, you always have a kind of left tail, right tail, or two-tail test, the interpretation, right? But for computations, since we are setting or writing the numerator by using the largest variance, we always want to be using the right tail test for computing our critical value or computing our p-value. In terms of p-values, now we're going to use 1 minus pf. Again, these are lowercase, as always, for every R command, R function. So it's going to be 1 minus pf parentheses, then we're going to enter the value of f that we found, then comma, then the degrees of freedom from the sample that corresponds to the numerator, and the degrees of freedom from the sample that corresponds for the denominator. So then, if you have a two-tailed situation, a two-tailed test, then it is multiplied by 2. So we're going to solve a problem now to apply this. And with that, we're going to finish our chapter 11. So the rest is just 2 more chapters, and we're going to finish our semester. So let's see. We're going to solve example 11.8 on page 555. So in that example, we're going to have the following. So let's read the example. So the example is here. We're going to read. In a series of experiments to determine the absorption rate of certain pesticides into skin, 2 pesticides were applied to several skin specimens. After a time, the amounts absorbed in micrograms were measured. For pesticide 1, the variance of the amounts absorbed in 6 specimens was 2.3, while for pesticide 2, the variance of the amounts absorbed in 10 specimens was 0.6. Assume that for each pesticide, the amounts absorbed are a simple random sample from a normal distribution, from a normal population, sorry. Can we conclude that the standard deviation of the amount absorbed is greater for pesticide 1 than for pesticide 2? Use the alpha significant level equals 0.05. So that's the problem. So now we just need to write the claim, the null. So the claim that we are trying to prove is that the variance from the first sample is greater than the variance from the second sample. What is the opposite? The opposite is just the variance from the first sample is less than or equal than the variance from the second sample. Then the alternative is going to be the one of these two that doesn't contain the equal sign. So my alternative is going to be this one. The alternative is the same as the claim in this case. The null is always one parameter equals to another parameter. In this case, the variances are the same. That's the null hypothesis. From the alternative, we know that this is a right tail test. So our F distribution is always asymmetric. So we're going to have something like this. So this is going to be the F distribution. So let's start, or let's continue by writing the significant level that we're going to use. Is just from the problem 0.05. We need to read carefully because depending on the significant level, the decision might be in one way or in the other way. So the next is we're going to compute the test statistic. So we're going to compute the test statistic. In this case, we're going to compute F. So F is going to be the variance from one sample divided by the variance of the other sample. This is the greatest variance, and this is going to be the smallest variance. Okay, so let's check the information that we have. The information that we have is from the first sample. So sample 1, sample 2. So the variance for 6 specimens is 2.3. For the second sample, for 10 specimens, we have 0.6. The variance is 0.6. So F, in this case, is going to be the greatest. So this is my numerator. This is the information for my denominator. So it's going to be 2.3 over 0.6. So we do these computations by using just a simple calculator, and we're going to get 3.83. So now we have two courses of action as usual. You either compute critical values or p-values. So let's say that we're going to use critical values. So alpha equals 0.05. So I have my F distribution. I'm going to find this value of F corresponding to alpha. So this region here is alpha equals 0.05. So to find this value of F, I'm going to use just QF in R, entering 1 minus alpha, degrees of freedom 1, degrees of freedom 2. So this is going to be QF of 1 minus 0.05 because alpha is 0.05, degrees of freedom from the sample from the numerator. So numerator 6 minus 1, those are the degrees of freedom from the sample corresponding to the numerator, then the degrees of freedom corresponding to the sample of the denominator. So in this case it's going to be 10 minus 1. So with this simple command in R, we're going to find this value here that we're going to use to determine whether our F statistic is in favor of the null or against. So this 383 is going to be somewhere depending on this value here, F alpha. Okay, that's the critical value method. So the p-value method, we're going to do a similar computation. So again, we have our F distribution. Now, instead of having a critical value here, we have our actual statistics from the sample. So now we're going to compute this probability here. and this probability is just 1 minus PF of F, degrees of freedom 1, degrees of freedom 2. So this p-value is going to be 1 minus PF of, and F we found 3.83. So we're going to write 3.83. Degrees of freedom from the numerator, 6 minus 1. Degrees of freedom from the denominator, 10 minus 1. So we're going to use now R to find these two quantities, both the critical value and the p-value, and then we're going to make a decision. And remember, regardless the method that you use, the decision is going to be the same. So for the critical value, you use QF. Remember, lowercase, 1 minus alpha, comma, degrees of freedom from the sample corresponding to the numerator, and now degrees of freedom from the sample corresponding to the denominator. So now I have my value of F, of the critical value of F is going to be 3.48, 3.48, 1659. Now the p-value is obtained by using 1 minus PF of my value of F obtained before. So that value is 3.83, and then degrees of freedom from the sample corresponding to the numerator and degrees of freedom from the sample corresponding to the denominator. So my degrees of freedom, my p-value is going to be 0.038, 85 to 46. So now I have two values to make a decision, and with those values I should get the same decision. So first, critical value 3.48. So this value goes here. So this is 3.48. Now where is 3.83? Is on the left or on the right of this critical value. You can see that 3.83 now is going to be on this region now. So it's in the region that rejects the null. So from this information, you're going to obtain the decision that you should reject the null. Your test rejects the null. So the test rejects the null. Now, in this case, if you want to use the p-value, you just need to compare alpha to the p-value, and you're gonna see that your p-value is less than alpha. So when the p-value is less than alpha, you always reject the null. So the decision is the same. The method that you can use is up to you. I like p-values, but it's up to you. The answer is always the same. So now we're going to write the conclusion. So now you can say that there is enough evidence to reject the null. There is enough evidence from both methods. By using the critical value method or the p-value method, we got the same decision. Now you know that the claim in this case is different than the null because you were testing that one variance was greater than the other or the other variance. So now you can say that there is enough evidence to support. We're gonna switch the verb because the claim and the null are different, to support the claim that, and usually you write here the claim. So what is the claim? The claim is that, and you write everything, the standard deviation, the standard deviation of the amount absorbed is greater for pesticide 1 than for pesticide 2. So that's the final conclusion. So you can see that writing the conclusion in terms of the null is very simple. You just write there is enough evidence to reject the null, and that's it. To reject the null that that the standard deviation 1 or sigma 1 equals sigma 2. It's very simple. It's just a mathematical symbol. But when you provide the conclusion about a test, you need to write it in terms of the original claim or in terms of the terminology that is going to be understandable by the person that is going to use your conclusions to work on other things. So now you're going to work on a couple of problems from the exercise set, and with that we're going to finish this chapter. So this is from section 11.4 exercise set on page 559. You're going to solve problems 14 and 16. So I'm going to show you now the problems just in case you don't have your book with you. So you just need to check then these problems directly from the screen. So I have here problem 14 and problem 16. So let me increase the zoom. Let me zoom in. So I have here problem 14. You have two samples, composite 1, composite 2. So you're gonna compute the standard deviation or the variance. If you compute the standard deviation with SD, remember you need to square that to compute F. And you can also use directly var over X of your data set. Var is going to give you the variance, but it's irrelevant. It's irrelevant whether you use standard deviation or variance. As long as you use the variance in the computation of F, that's fine. Then composite 2, you have to enter this as another data set, and then you compute the standard deviation of the variance, and then you proceed with getting your F, your p-value, your critical values, make your decision. Then problem 16, another two data sets, so another computations of variances from the first data set, from the first sample, and from the second sample. So work on these problems. Send me your screenshots through Canvas by using the corresponding classwork link and the submit button that you're gonna get there.